Yes, hello. Thank you. So yeah, my name is Nick, and I'm going to present to you the work that we've been doing at UC on Ejecta diagnostics and Plume-Surface interactions. So I want to acknowledge my co-workers on this project, and also NASA for funding it using an ESI and FINES grant. So next slide, please. So I'm not going to go over the challenges of PSI. I think everybody here knows about them. I just want to give you an overview of the PSI research that we have been doing at UIUC. So the idea is that we have a reduced scale experiment recreating the conditions of a lunar landing and Martian landing, and we use this to probe various aspects of PSI physics to improve our understanding and feed future models. So among the aspects that we're exploring, there's flow measurements using flat plate impingement and various visualization techniques, cratering and granular physics using 3D scanning of the crater. And also, what I'm going to be focusing on in this presentation is the ejecta dynamics. And so through the measurement of ejecta cloud concentrations and ejecta dynamics using PTV. So next slide, please. So the facility that we use to perform those measurements is shown here on this image. It consists of a cold gas nitrogen thruster, which generates a Mach 5 jet impinging on a surface of regular simulants. So in all cases, it is motor dispersed glass microspheres with an average diameter of 103 microns. And the entire assembly is located inside of a vacuum chamber for reaching subatmospheric conditions, which will be better representative of a landing on the moon or on Mars. So if you go next, you can see the chamber that we use, and if you go next, you can see the apparatus with the thruster and the grounded bed currently empty inside of the chamber. So using this system, we can target a variety of parameters. So those are the altitude of the thruster above the surface, the mass flow rate of the jet, and the ambient pressure inside of the chamber. And in this presentation, I'm going to focus on a specific case to show you the integration of two different diagnostics, so radar interferometry and PTV, to get information about the ejecta dynamics. So the condition that we're targeting is shown in orange, an HRVD of 3 nozzle diameter, a mass flow rate of 0.32 grams per second, and an ambient pressure of 6.7 Pascal. Next slide, please. So the first technique that we use, some of them may have seen that before, is millimeter wave radar tomography. So the idea here is that we use the fact that when particles are present on the propagation path of millimeter waves, when they travel between an emitter and a receiver, the presence of particles is going to shift the phase, is going to change the dielectric permittivity of the propagation medium, and this will cause a shift in phase of the electromagnetic wave, and we can. And this shift in phase is directly proportional to the path integral of the volume fraction of ejecta. So this is a very powerful technique because it allows us to measure concentration of ejectas independently of the particle size distribution. And it also does so at in conditions that would be completely opaque and inaccessible to an optical system. So in order to realize those measurements, we use a radar. So Texas instrument IWR-1443. That operates at 77 gigahertz with a repetition rate of 10 kilohertz. And in order to create those measurement arms in which the millimeter wave propagates, we use the radar in conjunction with a series of reflectors. So you can see here on the bottom right, sorry, an image of the radar, which is in the gray box, and a series of reflectors, which each generate a measurement arm on which the path integral of concentration can be measured. So however, what we are really after are local concentration of ejecta, and to convert those path integral measurements into local concentration, we use a tomographic technique. So by combining the measurement of all those 7 independent path measurements, we can back out the concentration of ejecta in local concentric areas around the nozzle axis, if we assume that the ejecta cloud is axisymmetric, which is a reasonable assumption since or tests are done with a normal impingement orientation. So if we do this, we can use an inverse Abel transform to invert those path integrated measurements into local concentration, as according to the equation that you show here. Next slide, please. So here I'm going to show you some of the results that we have obtained for the test case that I highlighted before. So the map that you see on the left are concentration maps measured by the radar. So how to read those plots is that on the y-axis is the distance to the nozzle. So as I said, it's an axisymmetric location. It's an axisymmetric. We assume that the class is axisymmetric. And on the x-axis is the time. So this presents the concentration measured by the radar as a color map as a function of position and time. And since this the system that we have developed give us the concentration on the slice that is parallel to the surface, we have repeated those experiments 2 times at different altitude. So the bottom plot shows the concentration at an altitude of 3 nozzle diameters, and the top one at an altitude of 6 nozzle diameter. And on the right, you can see a video, a high-speed video showing what this looks like in visible light. So yeah, you can start the video.
I don't think the video is playing.
Okay, so in terms of phenomenology, what we see is that the particles, which unfortunately you cannot see, are emitted from the edge of the crater. They then follow a ballistic arc, and as in terms of phenomenology, what you see is that this results in a very dense, localized cloud at the edge of the crater that is measured at lower altitude, and then at high altitude, the cloud is a lot more diffuse. Because the particles are arcing, they are following a ballistic trajectory. In terms of phenomenology, we also see that the angle of emission of the particles increases over time, and this results in a contraction of the jets, which again you can see on the radar, and you could see the video if they were playing. So next slide, please. So in order to complement those measurements of cloud concentrations, we wanted to measure the velocity of the particles. So in order to do this, we use a PTV setup. So we generate a laser sheet outside of the chamber, which we then beam through a viewport. The laser sheet is grazing the surface of the granular beds, and this vertical sheet goes directly underneath the axis of the nozzle. The particles that are lifted from the surface are illuminated and observed through an array of high-speed cameras, which you can see here. So we have 4 high-speed cameras, 2 main one, which is the Photon SA5 and Phantom V2012, and then 2 Chronos, which allow us to fill the gap at a lower temporal resolution. Next slide, please. So let's see if it plays, because you can see here that this is, yes, you can see. So this is a collage of the different field of view of our cameras, and you can see actually the phenomenology that we're describing with arcing trajectories of the particles and the increase in emission angle over time. Next slide, please. Next slide. Yes, so here I'm going to focus on the actual parts of the experiment that we've been able to analyze. So we have been able to analyze the data coming from the Phantom V2012. So do PTV analysis on those. We plot here the particle velocity and flight path angle over time. And what you could see in the video is that after an initial burst of fast particles, we follow with a more steady state velocity that evolves between 1.2 and 1.4 meter per second. And it does increase over time. As for the particle flight path angle, it decreases over time, which is coherent with the fact that the particles are emitted at an increasing ejection angle from the crater, and therefore have a steeper trajectory when they reach the phantom field of view a few centimeters away from the ejection angle. Next slide, please. Next slide.
30 seconds.
I'm going to pass this. It's not directly relevant, so you can keep clicking. Great. So in conclusion, we have designed and built a high-fidelity full-domain experiment to study PSI. And we have measured ejecta velocity and concentration using PTV, so well-established technique, and radar interferometry, which is a technique that we are pioneering. And those measurements allow us to provide insight into ejecta dynamics. So the next step here would be to integrate the measurement using an ejecta model, because if you have ejecta velocity and concentration, you have flux, and therefore a lot of information about ejecta transport and erosion. We also want to add real-time created depth measurements and extend the range of application of the diagnostic to flight instruments and non-PSI applications. I think I'm done here. Thank you very much for your attention.